So the title is Deep Reinforced Learning in Robotics, and the main idea is to see some basics about reinforced learning, deep reinforced learning, and application in robotics. So I am the head of the Robotics and Artificial Intelligence Lab at the Universidad de Chile. As in many labs, we have several robots, several applications, and we applied reinforced learning in many of them. So maybe what is different from our lab is our work in the automation of mining machinery. So we have worked on with all of these machines that you can see in the slide, and in the videos you can see how some of our autonomous loaders work in underground mines. This is a very challenging work because these machines are very big, so 10-meter longs, and the weight is more than 30 tons. So this is some of the robots in which we are applying different techniques, among them reinforced learning. So the agenda of this talk is first some motivation, so how to use reinforced learning, then some basics explanations about reinforced learning and deep reinforced learning, and then we will talk about the application in robotics using a case study. Okay, let's start. So reinforced learning. In the previous two talks, we have heard something about reinforced learning, but what is reinforced learning? So in one sentence, reinforced learning is learning by trial and error, or learning by interacting with the world. If we have more than one sentence, a paragraph, we can see that the reinforced learning is using as a methodology or as a framework the Markov decision processes. The reinforced learning addresses the problem of how an autonomous agent, an autonomous robot, learn optimal policies while interacting with an initial unknown environment. So in this picture, you see mouse. So the mouse needs to learn how to move, what to do in a maze environment. So the mouse has a model of the environment. This model is composed with states, and the mouse start interacting with this environment. So he observed the environment. So he get what we call observations. He act, so he execute actions, and he receives some rewards. So a reward could be positive or negative. So in this case, cheese is a positive reward. So how this works? So the agent needs to learn which actions to perform, in a given state. This is what we call a policy. So in this paradigm, basically the learning process is conducted by the reward. If you get rewards, given that you execute an action, that means this is a good action. If you don't receive a reward, or your reward is negative when executing an action, this means this action is not good for this given state. So this is a very basic idea. So maybe you will ask yourself, okay, this is another learning paradigm, but I already know how to solve many learning tasks. I already know that there are other paradigms, for instance, the supervised learning, which is the way in which you normally train deep networks. So this is just an alternative to that, or this is something different? Okay, so for answering these questions, let us see this example. Suppose you want to control this bicycle, okay? You want to have an autonomous bicycle. So how you solve this problem? First, you need to put some sensors, because for controlling this bicycle, you need to know the steering angle at any moment, and you need to know the inclination of the bicycle. And then, which is the task? The task is to, at any moment, to generate the control commands. In this case, the control of the steering angle and the traction of the bicycle. So if you want to solve this problem, using a controller that is based in machine learning. And if you want to apply the supervised learning paradigm, for this case, it won't work. Why? Because for applying this paradigm, you need to know at any moment which commands to send to the bicycle and how you obtain the information for training this learning machine. So it's no way for obtaining this data for the training, unless you apply a slightly similar, related paradigm, which is supervised learning together with imitation learning. In this case, you need something to imitate, someone to imitate, and but if this also is not available, then you cannot train this system. So how you solve this problem using reinforced learning? Okay, if you apply reinforced learning, you don't need to know the exact commands that you need to send to the bicycle, but you need to formulate the problem in a different way. And in this new way, this learning will be conducted by rewards. So you need to define the proper rewards, and the rewards will quantify how good the control is being carried out. So in this presentation, I will try to explain how this works. Okay, so the main idea here is reinforced learning in many problems is not an alternative to supervised learning. So try to tackle problems that cannot be tackled by supervised learning. So we will talk now about reinforced learning. As I already said, the general concept is learning by interacting with the environment. So it's a trial and error learning process. Which is the goal? The goal is to train agents that can act optimally based on their experience in the world when solving a task. So we take an agent, for instance, a robot. You let the agent to interact with the world, and in this process, or while doing this, the agent will be able to learn. And as a basic methodology, or framework, we use the Markov decision process, which is a natural way to formulate many of these problems, which have two characteristics. First are sequential decision-making problems. So you don't need to just give an answer at a given time, as for instance, in the case of the classification problem, but you need to give an answer for a process, okay? And the second characteristic is that you normally have uncertainty. Let us remember which is an MVP, or Markov decision process. It is composed of several elements. You have states. In this case, a state of the environment. This state corresponds to your model of the environment, or the model that the agent has about the environment. So then you have actions that will be executed by the agent. Then you have some probabilities. So the probability of moving from one state to another state, this is the transition probability. And then you have a reward not at any time, but in any state, you receive a reward for being at this state. Then you have a discount rate, which is a concept that means that the rewards have different value depending on when you get this reward. It's not the same to get a reward in this moment that in the future. It has not the same value. And finally, there is a policy. Yeah? A policy, it's an algorithm that a policy consists on the actions that the agent will select. It's a way of selecting actions given that the agent is in a different states. Yeah. So this is the general framework. So some few words about the reward. The reward is a scalar feedback signal. So the reward is defined by the agent. So by but by the human being that is formulating the problem, that is modeling the problem. The reward indicate how well an agent is doing or is solving a task. And the reinforced learning is based on the idea of having rewards, and there is a reward hypothesis. Okay, and this hypothesis said that that all goals can be described by the maximization of an expected cumulative reward. So now I mentioned the idea of expected cumulative reward instead of reward. So what is the difference? So let us say we are learning how to play chess, okay? While formulating this problem for an agent, you can define the rewards in different ways. For instance, every time that you eat a piece from your rival, you can define a reward. Or the reward could be, or every time you move a piece, you can define a reward for this action. But this is not what is relevant. For instance, if you move your piece from one position to another, you can receive a reward or not. But what is important is which is the impact that had this action on getting what you want to get, which is to win against your rival. So the expected cumulative reward is not is the benefit that you will receive when solving this problem by executing this local action. Okay, so I will try to explain this in the next 2 slides, or in two more slides. But the key concept is the reward. Okay, then the states. The state is, as I already mentioned, is the way in which the agent see the world. It's the internal representation that the agent has about the world. And what is very important is that the human being is the one, the designer is the one that defines the reward, the states, the actions, etc. But it's relevant that the states that are defined are a state that the agent can observe in the world. Okay, sometimes this is not so obvious. The policy is the way in which the agent chooses the different actions. But if you are more formal about this definition, a policy is a distribution of actions given states. So it's probably function that answer the question, given that I am in a given state, which is the best action that I need to execute. So now let us talk about this expected sum of discounted rewards. So it's a key concept in reinforced learning, which is the value function. The value function is a function that tells the agent the value of doing something, the value of executing a function on a given state. And this, of course, is not the same as the reward. This value function considers that the direct reward that the agent received after executing an action, but also all future rewards that will come when the agent execute the next actions. In this sense, this value function is a sum of the future rewards that the agent will receive after executing the current action and also the next actions. Okay, and here is where the discount factor plays a role. So, but if this is the benefit of executing this action and also the future actions, this means that you need to know the future for quantifying this value function. But this is not so obvious how you will know the future. But you have here in a given context, that is, you're working with an MPP, so there are different states, there are some probabilities of moving from one state to other state after executing some actions. So what is important to know here, or important concept, is that these value functions can be estimated recursively. So what is one of the main tasks of a reinforced learning system is to estimate these value functions, okay? And how you estimate these value functions? By experience. And after this Bellman equation from 1957, we know that it's possible to learn this recursively. So based on these ideas are implemented in different ways by different reinforced learning algorithms. So let us see one of the most famous, which is co-learning. Okay. First, let us see the general idea of the algorithm. So this is what the agent use for learning. So the agent starts on a given state is S, and while learning, it executes the following steps. First, given that it has this value function, the agent choose an action. Okay, an action given that is in the S state, and the action is choose using, as I say, the value function. The agent will try to maximize the value function. So after the action is choose, then the action is execute. So the agent interact with the environment. So given that the agent interact with the environment, the agent observe a reward. Okay, and then after executing the action, the agent is in a different state. So this is the way in which the agent update the value function for the state in which the agent execute action A. Okay, and these steps are continuously executed. So, but how is updated this value function? Okay, this value function quantifies the benefit of executing action A in a state S. So the new estimation of this value function is based on the old estimation, the estimation that the agent has before executing the action, plus this term. So this term quantifies what the agent learned while executing this action. So in this term, okay, we have a learning rate, as in most learning algorithms, and we have here what is here inside, okay, what we call the temporal difference. So the temporal difference is the difference between what the agent already knew, so the old estimation of the value function related to state S and action A with this term. What is in this term? In this term, we have the reward that the agent received while executing action A in state S, and this other term. This other term is about the future. So these other terms quantifies which will be the future benefits that the agent will obtain, given that executed action A and is now in a new state. So this is what we have in this line of the algorithm. And as I mentioned, the relevant is this, that the agent tried to improve its estimation of this value function by executing the actions and obtaining different rewards, and by doing this recursive estimation of the value function. So basically, what the agent is doing is the agent is filling this table. In this table, which is the value function, we have different columns, which are the different state and different actions. And what is in each cell is the benefit of executing an action given that the agent is in a given state. So if this table is already filled, for the agent it's very easy to take decisions. The agent is, for instance, in state 2, the agent can choose different actions, and which action will choose? The one with a high value, so with a high benefit, which is already in the table. So the whole process of learning under this paradigm has the goal of filling this table. Of course, when the table is empty, it's a problem because you cannot use the table, but you need to act. So the actions will be chosen using what is stored in this table. But if you are at the beginning of the learning process, you cannot use the table. So what you can use? So you will use the table, but people mentioned, and was already here, that the process needs to be epsilon greedy. What means epsilon greedy? Means that there is a dilemma between exploration, so trying to select new actions that you don't know which benefit you will get, and exploitation your knowledge. For this reason, the actions are choose using this idea of greediness. Okay, so sometimes you will use the value function of this table, and sometimes not, and that is a probability for this. So at the beginning of the learning process, you will choose actions randomly, and after you get knowledge and you start filling this table, you will start to using more the table. So at the end of the learning process, you will be using the table. If the agent, so the agent at a given moment will stop the learning process and will use only the knowledge that has already acquired. But at the beginning, it will not use the table. Okay, so this is the learning process. While applying this paradigm, there is some modeling issues. So the most important is, which is the reward. The reward needs to be chosen by a human being. And in many problems, it's not obvious which is the best reward that allows the agent to achieve a given goal. And also, there is the alternatives to use only very sparse rewards or use dense rewards. When the work of reinforced learning robotics started, people thought we will use just sparse rewards. This is, we don't want to give too much information to the agent, so let us go for sparse rewards. But nowadays, I would say that dense rewards are used a lot, okay? And many of the most challenging problems are solved by a combination of dense and sparse rewards. Sparse rewards means that the agent don't receive a reward in any state, but normally when the task is fulfilled. And dense rewards means giving constantly different rewards to the agent. And another important modeling issue when you design reinforced learning, when you try to that an agent use this paradigm, is to choose is that the agent need to be able to observe the rewards autonomously and also the states. Challenges, which are the main challenges? One, which is related with what we already saw in the previous talk, is that normally the learning process could be very long, and because you need to interact a lot with the world. But in some problems, as in the case of robotics problem, this can be a problem to having too many interactions with the real world. And the other problem is that we're using a table with state as columns, and actions as rows. But what happens if you have many different actions and many different states, or even if you have continuous actions and continuous states, then it's a problem. You cannot use this table. So how you answer these challenges? The first one, we don't want to use a table. So how to avoid using this table? By applying deep reinforcement learning, which is using neural networks together with this paradigm that I already explained. How we tackle the problem of too many experiments using simulations, okay? And also, it could be good to mix paradigms and to use together reinforced learning with imitation learning. This could speed up the process. Even you can use interactive reinforced learning. And there is other ways of answering some of these questions. So I'm not going to talk about this, but is the decentralized reinforced learning paradigm, the hierarchical reinforced learning paradigm, and also the offline reinforced learning paradigm. Okay, so let's go for deep reinforced learning. So how can we apply neural networks and how can we avoid using this table? So the basic idea is this table was for estimating this value function, okay? So, and this, so the idea is to approximate this value function. And we know that neural networks are universal approximators. So it's clear that you can use a neural network for approximating this, this value function. So you can have a neural network in which you can put states, actions, and give the value function, okay? And this solves the dimensionality problem, and this also allows having continuous inputs, continuous states, continuous actions. So this idea, so the idea of approximating the value function is not very new. Yeah, there are many different ways of approaching this, not only with neural networks, but the idea of using neural networks get very popular after this work in which it was proposed the deep Q-learning, so deep, yes, the DQN algorithm, and in which it was solved the problem of playing Atari games, okay? So the idea of these Atari games, for most of you are very old games, okay? So the idea is to have a system that can learn how to play these games. And how to play these games is how to give orders to the joystick for playing. So the actions are the orders to the joysticks. What the agent observe is the screen where the game is happening, and you need to have a reward. And a reward in this case is the points that you are getting while playing, or that the system is getting by playing. And why this was so famous? It was so famous because these systems achieve the same performance than the one that humans beings are able to obtain. So in some games, the system is better. In some other games, humans are better. But if you put all together, there is no big difference. So this I would say very simple system can achieve the same performance than humans. Okay, and these are the same or similar ideas than the ones that have been used for chess playing, Go playing, etc. So it's clear that this system can play in a similar way than humans, or even better, okay? In simulation, for the moment, or inside the computer, not in the real world. So, which is the basic idea of this, of how this problem was solved, I already said, by deep Q-learning, and how work this DQN algorithm. So as before, as I said, the traditional way of obtaining this Q function is having a table, and in the table you select you get the Q value of a given state and action pair by giving the state and the action. But in this case, instead of a table, we will have a neural network. Okay, and in this neural network, the input will be the state, and the output will consist on several different outputs, each output for each action. So if you, okay, this is for discrete state and discrete actions. There are other models for continuous state and continuous action space. But in this case, you put in the network an state, and the network give the Q value for each of the possible actions. And then what you do, you select the action that has the largest value. Okay, this is the basic idea. But the thing is how you train this network, because this is the network, when you use it, you put in state, the network gives different Q values corresponding to different actions, you select the largest, the action that gives the largest Q value. The relevant thing is how to train the network. So probably most of you knows how to train a network, how to train a deep learning model. And the key issue is to choose a loss function. If you have a loss function, you already have solved the problem, because how to calculate the gradients, how to propagate the gradients, etc. There is a machinery that can solve that. All of this is already automated. What you need to know is the loss function. So, but in this case, the loss function is more or less obvious. The loss function is this here. So you want to reduce the difference between a target value and estimated value. Which is the estimated value? The estimated value is the Q value that the network is giving you. Okay, this Q function is the value given the states. A is the action, so you have a Q value for each state and action pair, and this theta are the parameter of the network. So this is the estimation of the network, the current estimation of the network. But what you want to, this is different of what you want to obtain. What do you want to obtain? This term. This comes from the Q-learning algorithm that I already explained. Here is the reward that the system obtained, and here is this recursive way of estimating the future. So you want that after this training process, these two values are the same, so that you have a good estimation, and if these two values are the same, then you have reduced the loss. So at the beginning, when the estimation is not good and it's not estimating well the loss value is high, and you will decrease this using the gradient. So this is the basic idea. And this is reinforced learning. Of course, it's reinforced learning, but see that what we are using here for training the network is supervised learning. So your goal is reinforced learning. You are using rewards, but the mechanisms that you will use for training the network is supervised learning. Okay, but a couple of things need to be improved in order that this can work properly. First, so the two basic ideas is to use a target network and experience replay. So first, if you have this loss function, this is the way in which you will update the different weights of the network. Okay, this is the standard way of derivating this. What is the word? this is a standard way in which you apply the gradients and you propagate the gradients using this backpropagation paradigm. So with this, you update each all the weights, but there is some convergence problems if you use the same model for this estimation and for this other estimation. So for solving this, you will use two different networks. Okay, you will use a network that it will be updated in each step, and a different network that will make this recursive prediction. Okay, so you will use two networks. One is the target network, and after several steps, one network will be updated with the values of the other, and then you will keep using separate networks. So this is more, it's not something conceptual, but is required for obtaining convergence. And the other idea is how you use the data many times for the training. So, and this is the concept of the experience replay, which is then called replay buffer, and it's a table of different values. So you, every time that the agent execute actions, you store the state, the action, the reward that is obtained, and the next state of the agent. So you store this data, and while training the network, you use this data many times. Okay, so this replay buffer idea is somehow similar as the use of the mini batches when you train a network. Okay, that you use when you apply the deep learning paradigm, or as I said, when you train a network. Okay, so the idea of mini batches is here, and it's called replay buffer, and consists on using not just once the data of an interaction of the agent with the real world, but many times. So this is I would say, the most basic deep reinforced learning algorithm, the deep QN, but it's a family of algorithms for deep reinforced learning, but also for reinforced learning. But if we see the family of algorithms of deep reinforced learning, these families are somehow shown in this diagram. So first, all what I explained in this talk is model-free reinforced learning. You also have model-based reinforced learning. In the case of model-based reinforced learning, you use also models of what? Of the dynamics of the environment, of how the reward can be obtained, etc. There's different ways of using these models. So I would say in this moment it's more popular. It's model-free, but model-based is also very powerful. So you, in model-free, given that you use a model, you put a priori knowledge, so the training normally is reduced if you use a model-based approach, but you need a model, and many times you don't have a model. Okay, so, but model-free, very popular. In model-free, I explain not all the possibilities, but only the ones which are used which are based on having a value function. So these are the value-based methods. And if you remember, in this paradigm, you first estimate a value function, and after you have the value function, you evaluate the value function, you obtain a value, and according to the value that you obtain, you select the action. Okay, so the policy is related with the value function, but it's not the only possibility. You can work with policy optimization. In this case, you don't compute value functions, but you have a policy which is a parameterized function, and you learn the parameters of this function. So you can do reinforced learning without computing value functions. Okay, so in terms of deep reinforced learning, if you follow the value-based approach, you have here different algorithms. Which one I explained? DQN, one of many. Okay, here are only 4, but there are many others. Okay, if you follow the policy optimization idea, you have here different algorithms. Some of these are popular, and there are more. But it's also another idea. I don't have the time for explaining in detail, which is combining these two approaches. So if you combine these two approaches, then you get the actor-critic algorithms. In this case, you have an actor and a critic. The actor is the one that selects the action, and the critic is the one that computes the value functions, and both are related, okay? So you can combine these two approaches, and if you combine these two approaches, then you get these algorithms. For instance, the DDPG, TD3, or SAC. And these, I would say, in this moment are the most popular deep reinforced learning algorithms. So the ones that combine these two ideas. So they are very powerful. Okay, now robotics. So we want to apply some of these ideas in robotics. There are many different ways of applying these ideas in robotics. There are many different problems that can be addressed. So we will use a case study for explaining some basic concepts. So this case study is visual navigation of biped humanoid robots using deep reinforced learning. So the idea is that you have these humanoid robots, the nows play soccer, and you want that they learn using these reinforced learning paradigms to navigate. So for going in a safe way from one position to another position. So you will use a mapless visual navigation system. This is what we want to build. What means visual? Means that you will only use the camera. What means mapless is that you don't have a full representation of the environment. You don't have a map with the obstacles, because this is a very dynamic environment. So you only know where is the position that you want to reach. Then we are not going to use any detection or recognition algorithm. It's not that we will learn how to move, but we will receive information of other systems that detect the other robots, for instance. We don't want to do this. No. So our system will need to be able to learn everything. We are not using depth sensors, so we will not be able to estimate the distance to the objects. And for this specific problem, we have some challenges. One is that this work was done in 2017. So in that time, these now robots, they don't have any GPU. So this is a constraint. And the CPU is a low end, okay? It's an Atom 1.6 gigahertz. And also the robots have a very limited observability of the environment. They have a narrow field of view of the camera, just 60 degrees. So which is how we will solve this problem. Of course, we will use deep reinforced learning. And the idea is to derivate the motion commands of the robot directly from the color images. So only using the images, the robot will be able to derivate which commands to execute for moving. I already said that the training can be very long. So for this reason, we do most of the training in a simulator, okay? But as we heard in the former talk, we have the reality gap. Yeah, it's not so easy going from the simulation to the reality. How do we address this problem in this case? Okay, we have we solve the problem in a special domain, which is similar for the simulation and for reality. And which is this domain? We use not the real images, so the real images, so the images are different in simulation and in reality, but we use segmented images and low resolution segmented images. And in this case, the images are almost the same in simulation and in reality. So the reality gap is very narrow if we apply this idea. Okay, in this case, we will use an actor predict network trained using DTPG. So I just mentioned about the actor predict. This is the structure of the actor network and the structure of the critic network, and how we tackle the limited observability problem that the robot can see only 60 degrees. Okay, we can, the robot can move the head. Okay, so we will ask. So in our problem, how to move the head, we will be also learn. So basically, the robot will learn how to move in how to reach different positions. It will learn which is the speed in the x-axis, in the y-axis, how to rotate, and also how to move the neck of the head. And also, given that when you move the head, you need to remember things. Okay, for instance, there is an obstacle. You're seeing an obstacle in your right side. So if you're looking in another position, you need to remember that the obstacle was there. So for this remembered thing, we will introduce in this network LSTM cells. So we will introduce memory here. So this is standard in many problems that you in your network, which is normally feed forward, you put some memory. So we use that here. Then to estimate distances could be relevant for this problem, but we don't have we don't want to use range sensor. We want to use just the images provided by the camera. So, but we can do a trick that is used in many of these problems of applying reinforced learning in robotics problem. That is to use an auxiliary task. So in simulation, you can have more information. So in simulation, you can estimate distances. So when the system is trained in simulation, the network has more a second task to solve, an auxiliary task. For the actor, it's not only to estimate in the action or the action that need to be executed, but also an estimation of the distances. And the same for the critic, not only estimating the Q value, but also something related with estimating the distances. So when you train this network in simulation, you train using these two branches for the actor and for the critic. But that in reality, when you don't have this additional data, you don't use these two branches. Okay, but what the effect that is produced is that the network learn how to use this additional information when training for estimating distances from the RGB images. Okay. Okay, putting all of this together, which is the status. So these things are not obvious. So I mean, these things, which actions to have, which is you are, which state to have, and which is the reward, are things that the human designer need to choose, are not learned. Okay, so the action were much or less obvious. Are three actions related with the omnidirectional gait of the robot and the movement of the neck. The states are related with, or the observations that the agent will receive for estimating the state are related, also are the image. And then other sensor information. In our case, the robot has some touch sensors in the arms, and we use this information. Okay, so every time he touches something, he needs to learn that this is not a good behavior, so we need this information. And also the information of the target position. And as a reward function, this is what I told you before when I mentioned sparse rewards and dense rewards. This is I would say, a dense reward function. Okay, first, we need to penalize the robot when the behavior is not what we expect. So we penalize the robot when the arms collide with something, so with other robot, when the body collide with something, and also for avoiding this, when a robot is too near from an obstacle, which in this case is another robot. So these are all negative rewards. And we have a dense reward that is applied in each time steps, which is this function that rewards the robot in case that the robot is approaching the target. This is a continuous reward. Okay, we do this in simulation, then we apply this we test this in reality, and these are some of the results. In this video, for instance, you can see this robot moving among several other robots and going to the target. Maybe you would think, okay, maybe I could program something similar. It's not very amazing. Yes, but take into account that in this case, the robot learned everything from scratch. You don't say the robot, you need to avoid obstacles, or if the obstacle is too near, then turn to the right. Nothing. Okay? The robot learned how to solve the problem just by interacting with the real world. Okay, I said real world, but in our case, interacting with the simulated world, and then this is applied in reality. Okay? You don't have in this case a robot detector algorithm. Nothing. The robot learned that it needs to avoid other robots. Why? Because every time that the robot hit another robot, you penalize the robot. Every time that is too near from another robot, you penalize it. So you penalize all these errors, and you give positive reward if the robot is moving to the target. So this is the basic ideas, okay? But this is possible only if you are able to define a good reward. If you are not a very skilled human being, or you don't have enough experience, and you give a wrong reward, the robot will just follow your reward. Okay, so which is the challenging thing here? The challenging thing is for the human being, is to define the right reward. Okay, some challenges of the application of deep reinforced learning in robotics. The first one, remember the former talk, sim to real. Sim to real is not a solved thing. So why is this relevant? Because we want to solve or to train the systems in simulation and to apply in the real world. And it's not obvious how to make this transfer. So it's not obvious for any problem, so for all the problems, or for some problems, sorry. Then you need that this system can be adapted to new environments. So you want to train in a given environment and to use in a different one. And for some applications, this is not very obvious. Then this is transfer learning. What means in this context transfer learning? That maybe you learn to solve some problem, but you want to use all the knowledge that you acquire in a different problem. Okay? You learn how to manipulate objects and how to cook, but then you want to use this knowledge for moving, so for playing chess, for instance. So how to transfer the knowledge? It's not obvious. Then the training time is always a problem, okay? Because as you solve more problems, so you try to tackle more challenging problems. So it's always you are trying to solve more complex problems, and always the computer capabilities is an issue. Yeah, okay, and not only computer capabilities, but the thing that the interactions need to happen, and in simulations are faster than in the real world, but also simulations take time. Then as I said, the secret here is the reward. So, and how can we design good rewards? Then the idea of end-to-end versus parts. Let me explain this using the case of autonomous driving. If you have an autonomous vehicle, maybe you will think, okay, I want to apply this paradigm in an end-to-end way. So to have an agent that receives sensor information of the wheel, of the images, LiDAR, etc., and the system will give me actions, okay? But the problem is so complex that this paradigm doesn't work in a real setting. So instead, you define, you apply this in different modules, or you separate the big problem in small problems. And some of these small problems are designed by human beings. Some others are trained using this paradigm or another paradigm. So these big problems as autonomous driving until now are not solved in a robust way using the end-to-end paradigm. Then, as in any deep learning problem, is the thing of the explainability. So sometimes you want to know why the agent is taking some actions. Then is the thing related with uncertainty and safety. So in a neural network, you can never be sure which will be the output of the network, or it's not easy to be sure. So there are many people working in this, in the case of applying reinforced learning in the real world. So in the case that you can take an autonomous taxi, and this autonomous taxi, the controller was trained using the reinforced learning paradigm. Is safe? Can we be sure that will always behave as expected? Okay, this is a relevant issue. And also a relevant issue is applications in the real world. So I would say that until now, most of the work in reinforced learning doesn't apply in the real world. So in this talk, I mentioned how to apply reinforced learning in the real world, but many people work just in simulation or solving problems that don't need to be applied in the real world, as for instance, playing chess in a computer, okay, or estimating the value of stock markets, etc. So I think it's a challenge how to apply this paradigm in the real world. So here some reference. So I will give the organizers the talk, this presentation, and then you can maybe probably see some of these papers with more detail. So thank you very much for your time.
Thank you very much for the presentation. Now we can take a few questions.
Thank you. It was very interesting. Also, all the introduction on reinforcement learning. I don't know too much on reinforcement learning, so every time I hear this presentation, I learn a little bit more, which is very good. In the example that you show in the end, your application of the RoboCup, what kind of environments did you have in simulation? So how did you kind of randomize things? Like, for example, where you put in different robots around, could the other robots could be standing or on the ground, for example? I don't know. Okay. What kind of things did you envisage?
Thank you for your question. So in the RoboCup, okay, there are different leagues. So we're talking in this case of the SPL league, Standard Platform League, or Humanoid Standard Platform League. And in the league, we have simulators. Okay, there are already simulators, but these simulators are not very realistic. So they're somehow realistic in the part of the perception, but not in, for instance, in the how the robots work, etc. So many people train object detectors using these simulators, but it's always the reality gap problem that objects looks until this year, 2017, things looks different in simulation and in reality. I'm not sure right now how well are the simulators. So in the last 2 years, there is a great improvement in simulations tools. But in this case, we already have the simulators, and we don't use the randomized approach because, as I mentioned, if you use the original images, you need something like randomization. But you thought, we thought on the following: why not using segmented images and low resolution? And in this case, they look similar. So in this case, there is no reality gap. So this is our way of tackling this problem.
Did you need, for example, for the robot to then be able to cope? Because then when you show it in the real situation, the robot learns, let's say, to avoid the other robots, even if they are in different positions, right? So in the simulation, do you have to put the robots in different positions?
Yes, but yes, at the beginning. So there is also something that I didn't have the time for explaining this, but it's the curriculum learning thing. So one thing is that the agent is able to learn, but then you as human need to teach. So when you teach a child, you need to be a good teacher. So in this case, it's a concept of curriculum learning, that you start teaching the robot simple problems, and then you increase the complexity. So this is the idea of curriculum learning. So at the beginning, you will have a robot and maybe just one other robot, and the robot will try to avoid it, etc. Then you will build a more complex environment, and then more complex. And so this idea applies in this case, the curriculum learning concept, going from easy tasks to more complex ones.